approaches. So first to this species sensitivity distribution model that is called probabilistic species sensitivity distribution. You see on the left-hand side, let's say the geography of this R package that contains a few functions, and based on these few functions, also someone that is not used to model in R, everything is programmed in R, should be able to take data and compute the species sensitivity distributions. There are two ways. One way is to do it fully in R by programming the whole thing in R, and the other way, for people that do not want to code to program, they can take actually their own support information from an Excel file and link it to the software and just run the model. And as I said, I'll also give you an introduction into the general user interface that is a pure ETSS product. And I'll also explain when it would make sense to use it and when it is not meaningful to use such a user interface. Good. Well, let's go into the method first. You know, as Klaus already explained, these species sensitivity distributions are used to derive the PNEC normally. So the PNEC would be the 5% quantile. And very often you have a kind of theoretical curve that goes through your data and reflects, let's say, the biological reaction of a system that is exposed to a particular contaminant, and just lumps together the different organisms that react to this exposure. So in the case of nanomaterial, but also in other cases, we know that there is a large intraspecies variability, there is a large uncertainty on the lab experiments. We do not really exactly know what has been used. We do not know, well, we have difficulties to measure the reactions. And so the problem that we wanted to solve was actually that we did not want to use mean or median values for each species to create a whole curve for an ecosystem. And one way, and the idea was probably for the first time to compute for each species a known distribution. So instead of using the mean or the median for one single species, we in this approach produce curve for each species, then take all the curves that we have produced based on a stochastic, very simple algorithm together, lump together everything, and try to reflect the curves for ecosystems. I'll show later how this, I'll not show really how we do it, but how it looks like. Good. And what's the goal? The goal is actually that you want to use these curves to compare to realistic concentrations to get an idea on the risk that have to be quantified. I've also risk insurance companies that are interested in this approach, because this is, as I said, probably one of the first steps that go beyond this qualitative assessment, that do not really want to produce precision, but want to cover the whole possible spectrum on biological reactions, for example. So do not expect me to give you precise predictions on these toxicity reactions, but what we would like to do is actually to provide the whole possible spectrum in order to avoid risky events. And below you just see that risk is then computed as a kind of probability of exceedance of critical toxic values and the exceedance combined with the probability of exceedance of critical exposure values. Yeah. Okay. First, simulations were performed in 2013 based on a very small database. What you can see here is actually that although we do not know if we really got the right distribution, but more or less the distribution follows all the data that is available, so you're not far away from what has been measured, and you also see that you can extract the predicted no effect concentration. Right. So how do we do it? Just that the basic idea is that you, as I said, you not take the mean of each species, but you take all the data available, acceptable. Sometimes people are very critical to this approach and say, well, you cannot take until each standard is fulfilled. And my response is, no, I do not agree, because it is about risk assessment and not necessarily about to get the realistic curve of biological responses. You remember a few weeks ago in France, and I was contacted by a big concern, by a big company. I hope that they really have interest in France biotrial. Yeah, a few people that they died, I suppose. Yeah. I mean, if it is risk assessment, then it is clear you want to have an early warning system. You have to know, or you would like to know if something could happen, and you have to accept that you are at the beginning, at least at the beginning, not really exact, and that you probably would prefer to use weak data instead to do not perform risk assessment. Well, this is a big discussion, but I just wanted to underline that it is not about precision, but about to get the whole spectrum. So what do we do? On the left-hand side, you see that we just take all the data somehow acceptable from literature on one species. Then we build kind of uniform distributions. The nearer the points, the more realistic we suppose are the results. So you will get a high probability that this is the right area of values of your biological responses. And you then randomly produce a lot of values in these intervals, and you have also to consider the board somehow based on kind of triangular distribution. So you'll try to get the whole spectrum for each species, create the single species distribution, take these distributions together, as you see on the left-hand side, into this total ecosystem-based probabilistic species sensitivity distribution curve. Well, in order to do that, you need data, obviously, and the data that you could use is, for example, shown here, EC50, LC50, NOx, and other values. So the ideal endpoint for this kind of modeling would be the long-term NOAC, all right? So if you would have, or this is an equivalent to the HONEC, then you see then this model does not need any additional assessment factors. If you have long-term NOx, no effect concentrations, or then you just feed these values into the model. And normally, and hopefully you have a few of them for each species, then you just take everything that you have. If a literature paper provides you a, let's say, a range or a distribution, you can also take the whole distribution and feed it into the model. Then it just follows the distribution from the literature. So it's important to get the endpoints, and that's actually the whole thing that is needed on the data point side that you have to extract from literature. If you do not have these no effect concentrations, then you have to derive other endpoint data to transform them into these no effect concentrations. And to do that, we prepared 3 assessment factors based on the technical guidance document that we have on a European level. So the first one reflects the uncertainty long-term, short-term observations. The second one is the observed, no observed difference. So an EC50 is not the same as an LC50, for example, and has to be transformed into a NOAC by dividing, for example, the value by 10, but you are free to do something between 1 and 10. And the last one is a very interesting one, but in at least what I know, it is never used. This would be the lab nature differences. Well, it's ready to be used, but perhaps you know more than me. I don't know why this is not really used. So you have to derive the data, and okay. And well, in the model, this is just very simple. You have these 3 factors, and then I have to explain that in addition, you have to assess somehow the borders of each species. So the intervals are influenced now by these 3 assessment factors, but 2 are remaining. What to do with the borders? So you cannot say, well, I know the last data that I found just builds the lowest value. This is a little bit naive. So you have to use a kind of interval to go down, because you may expect that in future people will produce lower values. They do not try to go higher, obviously, because it's about reactions. but normally they become lower and lower and lower, but not under zero, obviously, no, a joke. Okay, yeah, this is the case for these assessment factors that you have to use. And here we just see one typical output of this software. First, the red curve is the, let's say, the species sensitivity distribution. However, you may repeat the whole modeling, for example, 1,000 times, and then the model just produces 1,000 species sensitivity distributions. So no theoretical computations on a confidence range or something like that. You just repeat the simulation. This takes a few days because, you know, just for the first one it takes a long time to get a lot of values for one curve. If you go on, you just do it, as I said, 1,000 times, and then you see what may happen. And why this may be important, I'll show you later. And on the right-hand side, you just see the cumulative illustration. Right. Well, in the end, this is just a fictional didactic example. Some kind of curve is produced in this software together with the illustration of the species that were used, the points. You may also add the median in addition to these points. You may do whatever you want to do. There is one problem, and the question is how to order these points. It's not so easy to explain. One could say, well, just build a mean. I did not do anything special in this case. It's something that has to be solved. I don't know what the best thing is to do. Probably to follow some kind of median. And what, however, although nevertheless, if it does not depend what order you choose, but what you see is that the curve really reflects the spread of all the points. But this is just a fictional example. I will show it in real examples later. Oh, sorry. Okay, was the wrong screen. And then another point that is an advantage of this approach, you do not have to compute the PNEC. You do not derive just one value. You derive from each curve that you produced one single PNEC, and you will get a curve of the PNEC. In a lot of cases, this has to be the 5% quantity. It could be something else. In LCA, LCIA, they need other points. You can do whatever you want, and the model allows you to compute the curve of this PNEC. So again, no theoretical computations on the interval, confidence interval of this PNEC, just empirically produced in this way. This is needed to compare to the exposure curves that are illustrated in blue on the left-hand side here. You just, and these are real examples, you just see that we compare the curves, the species sensitivity curves to the exposure curves that are red. And in a real example based on this software, this looks like you see here. So not anymore just one red curve, but all the curves, the whole range. Green, well, green is perhaps not the best color because it is not green, but just to illustrate you the range. And then you can compute the number of scenarios that are critical and compare these critical scenarios to non-critical scenarios. And also, in my eyes, the first time you could then compare your exposure to the PNEC curve instead of to one single curve. Good. Well, are there any questions before I'm going into the software demonstration? Good. It is late. Now I'm going into the software demonstration. Perhaps before I'm going to show you how it works. If someone then uses the model, you'll see on this slide that it is just brought into one single function in the end. It will be quite easy to use it if you have all the data ready. You go into one single function and you run then this model. Okay, let's see how this works. Well, you see here now the organization of this software. This software contains a kind of manual that has to be finished, but it is explained what's going on. I do not have to repeat it. I'm just going first to the main function, that is obviously the create the PSSD model. And you see again all the arguments that are needed. I'm not going to explain everything again. It is first the data that has to be there. And to take the data, you have a single function that is, for example, called load species data from Excel. And then this is a very simple function here. I just wrote it here, I did not want to lose time. You just say, well, my data is called tdata, and you then say to the program, load the species data from an Excel file, and it does it for you. And now I'm just going to show you the file. It's quite easy. In this R package, you may prepare extra data that is then, for example, Excel data, and what you have got in this file is then nothing else than all your endpoints, and the program allows you to do it for 100 species and to produce 100 endpoints for each species. It is rarely the case that you have so many data for so many species, but anyway, it's ready for that. And as I said, you may just connect it to your support information. It's not a lot of work to do. If you then have it, then you run the model. You call, for example, the vector, the probabilistic species sensitivity distribution. You have to choose the number of simulations. 5 is not too much. You have to use the length of one single PSSD. This means the number of values that you want to produce. You have to decide on the number of values for each species and on all the factors that I explained before, and then you just run the simulation and everything is done for you without that you see any codes. You do not have to focus on any real coding, and you can produce then these distributions. It will be ready soon. If you do not want to go for the Excel-based method, you then create the data yourself. So this means that you go into this, well, it's actually this one here, a very simple function that is called raw species data, and everything is ready. You then write down species A or something like that. Then you just write down your values. This species would have 3 values in literature, the other one as well, and so on. You just write it down for yourself. This makes sense if you can extract from literature whole distributions, then you just put your distributions into this function. Good. Let's see what happens if you have then this kind of function ready. Then you have a plot distribution ready that plots your results. If we go to the package, we see it here. Again, I created a few plot distributions that are also very simple. You take your PSSD that you have produced and can plot it. Everything is done for you. You can also plot the I plotted just so it was actually a simple plot with very few values. I prepared another one that would take a few, in reality a few hours to get it, but you have an impression what goes on here. Good, but as we know, this is just 1/2, and then the other part will be to plot based exactly on these computations, the PNEC. Has to be created first. To create the PNEC, it is also a function that is ready here. I know it's a bit late for that, but just to give you an impression. So the PNEC function is also extremely simple. You just say create the PNEC model for a particular simulation that has been performed. You just have to know the name of your simulation, then you use this function. Everything is behind the package and does not have to be coded at all. And then you may plot also your PNEC that has been shown before in the exposure computations. Good, and as I said, the goal was actually to do it in a comparison to the exposure. You need obviously your exposure data that yourself or your group has been created, or you could get it from others. Does not really mean. It's not important how you got these exposure concentrations. What I would say is actually that you need also for these exposure concentrations kind of curves to get a real stochastic comparison. And then you then just plot, as I did before, the curves, and not one curve, as often the case until now, but do it for all your species sensitivity curves, and you'll get more than one probabilistic risk curve. So the probability is, as I said, is here in this area where you see the exceedances of both curves. You could do the same exercise with the PNEC and compute the same risk based on the PNEC curve, or you may then combine everything. And if you combine everything, it looks like we see here, you have then everything. You may compare the PNEC curve and all the PSSD curves. Good. This is the PSSD part, and then going back to the state and flows part. No, I'm sorry, I forgot something else. There is a user interface for this method ready here. And if someone wants to use the user interface, then it is even more simple. You just select your endpoint for each species, write down the species name, write down what you found in literature, choose the metric endpoint, and so on. Go for the right assessment factors, add it to your raw data, and then you just run the simulation. Well, it does not make sense to go until the end. I have the impression that well, it does not work now with this nonsense data, but you can imagine what goes on here. In the end, you can plot the same curves that I did here, and it is extremely easy to use and leads you directly to results that can be used. I have to say that for research work, this is perhaps not really needed, but it could be needed for someone that has to produce a lot of species sensitivity distributions. So in a context of repeated simulation, I would go for this kind of user interface. Good. Because I have to hurry up a little bit, I'm going back to the flows and states part. That is the second part of my presentation. Again, I will show you first the method a little bit, go into a small, very short demonstration of the R package that is ready. Again, I prepared a way based on Excel data and another one that is a pure R-based way to produce flows and states of material. And the method should be used if you are faced with a lot of uncertainty, lack of data, weak data, and so on. This model has been, or this approach has been used to quantify probably the first probability distributions for exposure of nanomaterial in the environment, so for quantifying concentrations, or at least ranges of concentrations. And the flow model incorporates, as Klaus and Ralph already mentioned today in other contexts, for other methods, this kind of production of these emerging materials and the incorporation into applications, products, and then of course the release. And to some extent also fate in the environment is, at least where you have to decide what is transferred between compartments. A real fate modeling has not been performed based on this method. However, in 2014 it has been performed on a dynamic level for fate of nanoparticles in a reactor in an incineration plant. And the method actually bases on a very simple idea that something can be transferred between geographical locations, material states, and the transfer is always between 0 and 1. This keeps the whole error propagation under control. Otherwise, if you use this full stochastic approach, you will end up with just with an error propagation that leads to something that cannot be evaluated anymore. But since we reduce almost everything to these 0 to 1 transfers, this can be controlled very well. So the software contains the possibility to have 50 main material states or locations, and in each material state or location you have 4 sub-boxes that may reflect unknown fate, just because you are not able to detect something for nanoparticles, for example, or a kind of delay of the further transport into another location, or a sub-box for elimination, transformation into other compounds, I don't know what, or a kind of deposition. And obviously you may combine everything between these material states. So in the end, in principle, the method contains 250 input values, but obviously you do not have to fit these values into the model. They are just ready, and as default they are 0, and everything that you have, you then add to the model and run the model. I explained, one important point is that you may reflect in your modeling, in your flow and states, material states modeling, not detected parts. This is important for these new materials, or parts that are not transported further in a particular time. If you have to consider residence time of particles in rivers or in different parts of a reactor in technical compartments, you may compute the flow rate, and the position transformation may also be integrated. So sometimes if you take a dynamic perspective, then after a few hours or days, your system will go into an equilibrium state. And for other situations, it will just go down to 0 values, as you see in the second example, or it may also be that you did not find anything in the 4th example. So different kind of time-dependent behavior is possible and can be computed. You then extract at each time, if you want, you may evaluate the statistical results at each time point. That's possible, combining with the time-dependent dynamics that you see here. Good. If we then later go into the software, it's already mentioned here, you need 3 different data levels. First, a kind of input of a particular material into your target system. And everything that is quantified in the input data has to be done based on a probability distribution. 5 examples have been prepared. It can be that you select a uniform distribution. For example, this is just an example. If you just know the borders, could be that you go for a uniform, for a triangular one. If you know a little bit more than your extreme borders, but you have a kind of tendency where you say, well, this is the most probable value, you go for a normal one. For example, if you've got a lot of, or let's say sufficient amount of values, and you know something about the way the low probability tails and so on, or if you go for bootstrapping, this is the way to go. If you have a lot of very, let's say, somehow reliable data, then you say, well, I do not want to construct any theoretical curve through our data, just go for that data that I've got. And sometimes you may combine it, and then you end up in a kind of Bayes approach. You do it for everything. Now I explained it for the first part, for the material input. That can be a production of material or a kind of import into each main box in this system. Then you have to do a kind of distribution of material into applications. This is necessary for this nanomaterial studies or for other material that is used, because the material will be used in product before it is released to nature. Then you will just decide on what materials you have data. You have to decide on the percentage of the material produced that is used in this data. And in the last part, on the right-hand side, you then have to give input data for all the transfers into nature and between natural compartments, as well as between technical compartments. And that's actually the whole exercise on the material input data preparation. If you have everything, you may run the model. One point is extremely important. It is not difficult to use this kind of models, and this applies for the toxic part as well as for this release fate flow model part. But you have to think about what you do with these models. You know, everything stands and falls with the data, although you may do a little bit more than a deterministic approach can do. So what I want to point out here, to underline here, is that you have to be careful what data you use. Think about the quality of the data, because if you select the distributions, you influence very much the output, so you have to have reasons to use these distributions, and you have to know a little bit what you do. This is just to tell you to be very careful, and in my eyes, we should not communicate single scenarios as you see later, at least for nanomaterial, because we just have to we do not have the data quality, and we do not have the data quantity to do that. This slide just summarizes everything that I explained on the selection of the distributions. I do not want to repeat everything. I tried to produce a kind of decision tree for that, and I saw that this is simply too complicated. And then, as I said, it is the task of each one that uses the model to think about what he or she does with this data. But this kind of decision tree can be a kind of initial orientation. And I'm not going to repeat everything on that. But another point is extremely important. If someone performs this kind of simulations, it is not okay to extract just one single scenario that is mathematically fine, but it is just nonsense. The output is a curve, and in principle nothing else than a curve for each single simulation output. You may go for the mode value, for the most frequent value, that is the red one here, but much more cannot be done based on these computations. Good, this is one typical output, a kind of flowchart based, for example, on the modes. And another one is the same flowchart based on the whole curves, that can be then used to quantify the concentrations, and the concentrations are just quantified by distributing the particles or the particle mass into a particular compartment. You then may evaluate it statistically by considering a kind of interval. Whatever you want to do is possible then in this software. Good. Let's go to the last demonstration. First, the package is ready here. Again, it contains a description and later a kind of manual in order to use it. The main function is called to create the PMFA, that is the probabilistic material flow analysis model. It is the name based on the method that was first realized, but it is a little bit, perhaps not the right name. I would say it is a flow and material states model. But as you can see here, it is, again, extremely simple to use them later, because the only thing you need is your data. I've shown you that there are 3 data levels. And you then decide on the number of simulations and the time that you have to use. If you go for a dynamic version, you have different data for different times, and then it becomes a little bit more complicated. Today I will just show the equilibrium case on a few examples. Take from here. Okay. First, you have installed the package, then you load the package, and again you have these 2 ways to take data. The first, and I would say the pragmatic one, is that you go for a kind of Excel file that contains everything, and again this Excel file can be prepared in your package, and I'll show how it could look like. Well, you see a possible, very simple file where you can decide first, for example, for the material input between the distributions that have been shown, and then just write down the values that you have. This is probably the best way to go. If you have single values, you will never have too many values. It's quite easy to write it down. You do it the same for the distribution into applications. You have a lot of different applications, and you have to do it also for the natural compartments in the second level to have this kind of release from the production part to the applications and natural compartments. And on the third level, you have this transfer between all the compartments. And again, you just select first your desired considered distribution, write down the numbers, and then that's it. And then you go back to your package, run the package, load the data level, and if this has been done, you just need to use the main function that is create the model itself. Then you run the model. This takes a little bit time. That's the reason why I'm actually directly going to another saved computation. And if you have run the model, you then just produce your plots, you quantify your results. This can be done, for example. Okay, yeah, this is done for example this way if you want to go for this flowchart. Otherwise, if you just want to get single outputs, you can then choose one single box and say, well, I want to know, I want to see the curve for one single transfer. And this should be done. Sorry, now it's going to repeat the first part. Just 1 second, and then okay, well, there is some demonstration effect here, don't worry, I'm sorry. It's not so important to see. Anyway, what I wanted to say is actually, and I'm not going to show you because it seems to work, to run, I don't know why. But anyway, what you can do based on this software, you can then produce for each single transfer or material state that you see here, a known distribution. I'll explain to you what goes on here, that the values that you see here, for example, is actually the transfer, and the values that are inside the boxes reflect the position on or other kind of transformations of material. Good. I'll go back to the R shiny. but this is obviously the demonstration effect. Go back to that. Okay, good. In the user phase mask, you see the input data that has to be used. You can write down the name of your material. You have to decide on the input, on the metric unit, on the values that you need. You just write down your values, and software then produces the distributions selected. You do it for the material input, as I explained before. You do it for the distribution into applications, as you see in the middle part, and you do it for all the transfers between the different natural and environmental compartments. You select your compartment, you select your distribution, your fate, that can be the deposition, unknown fate, transport delay, or it could be something else that can be prepared, and you then plot all the concentrations, show the data table that is there or is not there in this case, because we do not have too much time to do it, and because I have to finish now. But anyway, also for this probabilistic material flow analysis, I have this software ready, and I would say also in this case the user interface should be used for cases where you have to repeat your simulations, otherwise you go for the R package, as I showed before, that is there for research and can be adapted for own needs and is organized with a few very simple functions, as we can see here. Good. To go back to the presentation and to finish it, I have to go, and I lost the slides, but I will find them again. Conclusions. The R packages are almost finished, but not really. I need some kind of finalization and then probation period, perhaps together with interested partners. I do not know what to do exactly. The general user interface, the same, but this is something for someone that is really interested to use it and not finish it just for something theoretical. This has to be done for a particular project. And this applies actually to the toxic model as well as to the probabilistic material flow or flows and states model. And the term of use is not specified as well. Could be that I'm going to publish the R package, but this is an open point. And as I more than once explained, the GUI is focused on commercial stakeholders. Good. I would like to thank you for the attention. Now it's late during this very interesting and hard day. I really thank you for listening to me.